Welcome, everybody, to the Land Aware seminar series. Um, Introduce myself, Corey Fraze, my colleague Lisa Luna. We've been coordinating this series. The intent is to have a monthly webinar on topics ranging from new innovations, actual case histories, communications, and also highlighting some of our early career professionals. So we try to get a mix on a monthly webinar. Webinars, of course, are uploaded to our website and on our YouTube channel. So please encourage you to let others know about this series. Today's talk is going to be from my friend and colleague, Davide Bertolo. Davide formerly was the director of the Geological Survey in the Aosta Valley in Northwest Italy. And he's been involved with a large variety of local and regional landslide characterization, risk management, mitigation, early warning projects, just a vast amount of experience. And I first met Davide in 2013 when we had a workshop on landslide early warning and planned it for Corma area, Italy, right in the, and at the time we did not know that we would be in the middle of an event where the village was evacuated, and we were actually able to visit the site and meet with Davide and his colleagues. So I thought for this group, just getting some of that experience from early warning, it is messy, it is complicated, it is fun. And I think Davide will give us a really nice overview of that. So Davide has recently left the Geological Survey. He is on his own as a consultant. He has his new consulting company, K4T, Knowledge for Tomorrow. And I leave it to you, Davide, to let us know about your experience at Mount de la Saxe.
Okay. So thank you. Thank you, Corey, for introducing me to this webinar. And thank you to all the Landaware guys and people to give me this opportunity to talk about the Mont de la Saxe landslide experience that, as you told earlier, led us across the years, across many years, and started to be consistent more than 10 years ago. And briefly, I am a geologist, and as you told before, I was for 14 years the responsible of the Regional Geological Survey, and before that, I was also working as a manager in the civil protection field in my former administration. Okay, so let's go into the core of our presentation today. We will walk across these main topics, the context and constraints first, some general clues about the Mont de la Saxe landslide, and the second, why the system is complex, kinematics and hydro control. The third point, and a more genuine land-aware topic, it will be monitoring architecture and why redundancy matters in a monitoring system. The fourth is we begin a reflection about why the threshold failed, comparing 2013 and 2014 experiences. And the fifth topic is the takeaways and how we moved from to multi-evidence decision-making process. And finally, some word about the how we can exploit the results of this of our experience. Okay, let me start with a simple statement. Monitoring generates data. Data, hopefully, provide information, and decisions generate consequences. In landslide early warning, our job is not to collect more time series. This is more a scientific interest. Our job is to decide when do we shift from normal operations to emergency actions. This is the main question. So, translated, when do we evacuate? When do we close strategic infrastructures? And at La Saxe, this question is central because the slope threatens communities and strategic connections. So, not only the monitoring system, but also the early warning system must be reliable, auditable, and usable under pressure. That's the real challenge. And so the topic, the main question, another main question is when is it time to act? Okay, and so some information about the Mont de la Saxe landslide. It is a slope instability located in the northwestern corner of Italy, at the border of Italy with France. This is the Mont Blanc Massif, and Switzerland. It is located on the northern side of our region. And as you can see, we are in a very congested area, classical situation of an alpine valley. This is a caption from a screenshot from Google Earth, where you can see the landslide location inside here. Okay, and this is the situation that we began facing in 2012. Mont de la Saxe landslide involves about 8 to 8.5 cubic meters of unstable material, and the slope instability threatens strategic infrastructures. Namely, this is the Mont Blanc tunnel. This is the southern gate of the tunnel. The dashed yellow line is the A5, is one of the most important motorways that are linking northwest Italy to France. Okay, and the touristic resort. These are two hamlets in Courmayeur. These are non-incorporated hamlets that are belonging to the municipality of Courmayeur. And in this context, there is also a very important investment that is the new Mont Blanc ropeway. That is an investment worth 160,000 million euro. And as you can see, this is a traffic flow map. The Mont Blanc tunnel is a very important communication access between the northwestern industrial zones of Italy, Piedmont, Lombardy, and the southeastern part of France. And so, in this context, false alarms are extremely costly. We have a real estate value that is evaluated at about 400 million euros. And stopping the traffic at the Mont Blanc tunnel costs about 2 million euro per day as damage to the Italian economy. And these dual constraints formed the backbone of our work during the years. And okay, it's not working, but I will activate this. Oh, nice. This is a computer simulation of the invasion area performed in the 2012. Now is a bit reduced, the area, but as you can see, the bottom of the valley floor could be covered by a debris cover up to 7 meter thick, and the motorways could be severely hit by this event. And not to miss anything, in 2014, the landslide, the unstable slope, partially collapsed, and a sector of 450,000 cubic meters collapsed, but hopefully not invading the valley floor. We will talk about it later. Okay, this slide explains why decision-making is so difficult here. We just said that there are two exposed hamlets and a major touristic asset. And we have the Mont Blanc tunnel, the A5 corridor between Italy and France. And we also have a key constraint. Infrastructure relocation is impossible. So risk must be mainly managed through monitoring, mitigation, and civil protection planning. That dual constraint is the backbone of the whole early warning strategy. And this is a quite common situation in the Alps because the Alps are a very congested chain with a lot of population, infrastructure, very narrow valleys, so very no room for relocation. Okay. The geological setting highlights a multi-domain system, and this is the core of the core geological concept. You see the slope includes multiple kinematic structural domains with different velocities that are ranging from 20 millimeters per day, the most active sector, the C, one that behaves nowadays like an airflow, but with a slower sector that are with a displacement velocity of 20 millimeters per year. And even in depth, we have a deep active sliding plan, typically between about 50 and 90 meters. And this matters that a multi-domain system doesn't behave like a single block. So signals can be ambiguous. One sector may accelerate without global failure, both in surface, such as in this case, but also in depth, because we can have superficial displacement if this plan, for instance, becomes active, or larger activations if it's the mine sliding plan that is active. Okay, so you can see here two core samples of the mine sliding plan with about 5 to 10 meters of completely fragmented material, almost cataclastic and myelonitic, and with the clayish rocks. And you can also see that you have, in some cases, two groundwater tables, and in addition, multiple sliding planes that is confirmed by the inclinometric graph that you are seeing on this slide. So, okay. This is the core reason why decisions are difficult. We are not dealing with a single landslide, but with a system that is composed of multiple kinematic domains, and each one is behaving differently. We have different velocities, different rheologies, and a deep active sliding plan that we cannot directly observe. It doesn't surface. So when we receive a signal from the monitoring system, the key question is not is the slope moving, but is which part of the system is moving. And this changes almost everything, because in a multi-domain system, signals are inherently ambiguous. One sector may accelerate without leading to collapse, or a local failure may propagate and trigger a cascade in nearby sectors. That is why point-based monitoring is not enough, and why decision-making requires special understanding of the system and a comprehensive geological model of the slope. So now we dive more in the dynamic and into the behavior of the landslide. Okay. The value of the assets that are threatened by the evolution of the landslide justified the installation, the implementation of a very robust and expensive monitoring system, and designed to deal with this complexity, and with the RTS, robotized total station targets, continuous GNSS, multiparametric DMS ground probes, ground-based INSAR radar, and automated rockfall detection. At the first glance, it looks redundant, but as you will see later, redundancy in this case is not a luxury. It is a way to control uncertainty and to cross-check signals and keep monitoring operational under different environmental conditions, namely meteorological events that in the Alps are, the weather is very variable, even in a single day, during a single day. So this is the conceptual scheme of our multi-technology monitoring system, and how we think about it. Some sensors detect surface movements, others provide depth information, okay, and other provide spatial pattern and aerial involvement. The key is not the sensor itself, clearly. It is the combination that allows us to move from displacement, like in this case, with these punctual instruments, to scenario, as we will see in the next slide. So to transform a datum into a civil protection information. How much thickness, which domain, what volume, what runout area. All is dedicated, as I said before, to move from uncertainty to risk. That is a very important leap. Okay, this slide shows how raw monitoring data, such as in this case, this is a GB-INSAR map of the displacement on the unstable slope with a very active area. Okay, and the monitoring data is translated into actionable decision making. This is the bridge between measurement and response. So the map on the left is telling us where the movement is concentrated and how it is evolving spatially. It is still confined to the core, or is it still spreading to adjacent to nearby sectors? In the center, we have the inclinometer depth profile, the modulo dello spostamento, like it's called in Italian, okay, the formation module plot. And this is one of the most critical instruments in the system because it shows displacement as a function of depth, and it allows us to identify whether the movement is shallow, like with a shallow surface, or is deep-seated. And the depth and shape of the displacement directly determines which event scenario is most probable, is most likely. On the right, you have the scenario map and the operational output of the entire monitoring system. Two perimeters are drawn on the topographic map, okay? And in this case, the black perimeter corresponds to the limited collapse event that can lead to a limited application of the civil protection plan with less discomfort and without closing the access to the tunnel or a limited closing of the access to the tunnel, whilst in the total collapse event, you will have great damages and the worst. This is the worst case scenario. So the monitoring system identifies the most likely event scenario in near real time, and this is why integrated monitoring matters, not just to measure displacement, such as in this case, but to determine which scenario is evolving in real time, so that the civil protection response can be proportionate and timely and not just reactive and blind. Okay. Now I spend some word about the real quote unquote propeller of the landslide. Okay, propeller is more or less the gravity, but I saw the lubricant. Okay, the second propeller is the water. This is a cornerstone insight, because the groundwater level peaks occur during snow melt. As you can see, this is a graph that is showing you displacement trend. That is the red line on one optical target. This is an optical target where the trend is very clear, but we have many other optical and other virtual points that show the same behavior. And you can see from 2015, from mid-2014 to 2021, and you can see that the acceleration occurs during the springtime, and then it is coincident and strongly correlated with an uplift in the groundwater table. The groundwater table is the blue line. It is measured by the ground probe DMS-7. In this case, we are at about 85 meters below the ground level. So what is very interesting is that the acceleration occurs when the groundwater table raises up to interest to catch the sliding plane. So when the groundwater level decreases down under the sliding plane surface, the phenomenon is slowing down. The slope is slowing down. Okay, so seasonal acceleration driven by snow melt and spring precipitation. This is snow melt. The main controller is only snow melt for now. In the future, with the degradation of the rocky mass, probably the scenario will change, the driver will change, but for now and for many years in the future, it won't change anyway. Groundwater peaks consistently precede velocity peaks. Okay, you can't see it now, but I assure you is so. So the anticipation is more or less, the advance is more or less 2 weeks. Okay. So in this case, we decided to implement. We had all the evidences to implement a water drainage system just to mitigate the evolution of the phenomenon. And Another takeaway is that when a phenomenon is so critical, when an unstable and a slope instability is so critical, it is almost mandatory to monitor the groundwater with a continuous monitoring system because it can be a source of vital information to exploit and to manage better the monitoring system. So drainage, as I said before, is the primary mitigation measure applied to the Saxe landslide by reducing the pore water pressure deep in the rock mass. We directly reduce the driving force behind the slope instability. And so we performed two main campaigns of two drilling campaigns during the period during 2013-2015 and in 2018. We deployed over 5,000 meters of sub-horizontal borers from 100 to 300 meters in length and targeting the saturated zone and that we had identified by monitoring system and geological detailed mapping. And the map on the right shows here, you see the fan shape, the geometry, fan shape geometry of the draining boreholes. Okay, and okay, the intervention achieved about 80% success rate. That is 8 or out of 10 boreholes intercepted and actively drained the water. And this is an high yield for deep drainage in fractured rock. We were pretty lucky, I would dare to say. Critically, the effectiveness of the drainage was not assumed but verified. Displacement monitoring confirmed a measurable acceleration in slope velocity following each campaign. And as you can see in this slide, mitigation from 2013 to 2015, the drained discharge increased and reached the actual volume that is from about 3,500 up to 8,500 cubic meters of water per day, depending on the season. Clearly, the highest value is in the snowmelt season, and the average velocity has been reduced of about 4 times, as you can see from the full activation of the drainage. You see also that these acceleration are more feeble, even though the landslide has not stopped, because there is a creep, a dry creep component that is still active. So, just to sum up, in this case, this slide brings together everything we discussed so far into a single picture of what each sensor actually contributes to decision making. So if we examine the table row by row, we begin with surface sensors, RTS, GNSS, INSA, and they tell us where the slope is moving and when it starts to accelerate. They give us the spatial extent of the affected area, and typical are our first alert. In-depth probes, the DMS inclinometers answer to a critical question. It is the depth sliding plane involved. This determines whether we are dealing with a shallow manageable event or a large volume, potentially catastrophic collapse. Without this, we simply don't know the true risk. And we have other instruments to give us the aerial picture and so on. Piezometers close the loop. They tell us why the slope is accelerating. And by linking displacement to groundwater fluctuation, we move from observation to understanding of the trigger mechanism. And this is the key point of this slide. The integration, as I said earlier, integration is vital for to have a very performant monitoring system. No single sensor gives you the full picture, but when you combine all the sensors, you shift from saying, okay, the slope is moving, to being able to say, okay, scenario B is most likely than scenario A. And this is what drives a defensible and timely decision. Okay. And that is more or less the goal of the entire monitoring system. So now let's dive into the most sensitive part of this webinar, and this is which are the takeaways we have now. We have everything is going well. Okay, with the decision, we show you the decision logic, no? Event scenario, two targets mean risk, so we can activate a civil protection plan. We have the areas to evacuate, and in the end, if necessary, the tunnel closure. So monitoring this is designed to evaluate in near real time the deep evolution of the landslide, to understand which scenario is most likely. So the output is not a velocity value, okay, as I said before, is operational scenarios. And now everything is going fine until now. Because 2013, when for the first time I met Cory, it is where the story changed. And you see, you have a look to the what was the operational early warning structure, more or less as a traffic lights architecture, green, yellow, orange, red, each associated with the internal activation, external alerts, and so on, up to evacuation and closure. Now, this looks standard, but the real question is, does a traffic light system or any other system based on a single threshold produce a reliable decision in a multi-domain landslide? And this is where La Saxe taught us the most important lessons during these years. Okay, you see already here that we trespassed the alarm threshold for nearly 2 months. Okay, and have a look to this slide. That's what happened in the spring 2013. The threshold is the threshold of velocity calculated on optical targets. On the average velocity of the last 24 hours. That's the meaning of V24, and this is a quite common threshold, quite a widespread threshold, widespread value. I should say, I would say in the monitoring world. Okay, 1 millimeter is a warning. 1 millimeter per hour is warning. 2 millimeter per hour is alert or alarm. Depends on the rules that you have in your country. Okay, in 2013. V24 exceeded the alert threshold and reached about 7 millimeters per hour, remaining about 2 millimeters per hour for roughly 60 days. And according to the threshold based the early warning procedure, at that time, this meant high likelihood of collapse. So we evacuated, closed infrastructure, and activated the protection plans. Only the tunnel remained open, but nothing happened in the end. And people were evacuated for about roughly, as I said, 60 days. And this creates a fundamental question. Is the problem the threshold itself or the reliance on a single threshold logic? Let's have a look to what happened in 2014. In 2014, I didn't say that the sector that already accelerated was the sector C, that is this one, okay? And 1 year later, in 2014, the slope accelerated far more intensely. V24 rose to extreme values, up to around 500 millimeters per hour, half a meter per hour. And a collapse occurred about 45 days of accelerations and decelerations. We evacuated again, clearly, but we already had some lesson learned, and so we decided to stop the traffic at the tunnel only for 1 day, just before the final collapse of this sector. I can show you a time lapse of this of the collapse from this is a time lapse from March to May 2014. Okay, let's go. And here we are. I show you again, but you can come back on YouTube. And we were lucky because all in all, the real collapse, the real rheology was less brittle than what we guessed before based on the model. So the propagation, the runout area was not so large as we predicted. Okay, but nevertheless, as you can see here, we had many reasons to be concerned, because when the acceleration of the sector C, kinematic domain C, began, we observed also an acceleration in the nearby sector. You can see the overhanging sector B that was sensibly accelerating. Okay, the sector A also showing acceleration, and the sector the nearby the sector on the right, that is actually on the left on the slope, the sector D, that is the great landslide that can collapse, showed a slight acceleration. Okay, so we observed a recall effect, and with deformation that propagated across nearby domains. The slope behaves as a coupled system with a potential multiple sequential failure scenario. So the lesson learned is that the early warning cannot focus only on a single point. As we said, it's quite trivial statement by myself, but it is a further evidence that is true. Okay, it must represent the behavior of the whole system. Another interesting point was that we tried also with all that data to perform and on the go and a prediction on the go on about the the deadline about the time of collapse using the inverse velocity method, also known as a Fukusono method. And what we got were three different time of failure. The first one was March 28, but after this acceleration, you can see that the landslide, the active sector, slowed down. So it accelerated again. So we got another time of failure at April 11th. And in the end, the last prediction was for April 17th, and just to have a final collapse on April 22nd. So all this stuff, triggered and stimulated a lot of reflection. Why? Because the first, because we are going into the lesson learned and the new system that we implemented and the new way to approach monitoring system for large landslide and other objects that you will see later. And okay, just to begin our approach, you have to take into account, and I strongly just suggest you to read even a condensed version of the book from Daniel Kahneman. He was an economist, a Nobel Prize for economy, that coined the term of cognitive biases. And its book is Thinking Fast and Slow, is very, very important. And I strongly suggest to take the time to read it. But when you are in the decision room, with a very performing monitoring system, this can be sufficient. Emergency decisions are also affected by cognitive biases that are risk aversion, overconfidence, and confirmation bias. After just to name three of them. And after a false alarm, the temptation is to shift and to fix the problem quickly. You are under pressure from people, stakeholders, administrators, and so on. And the first solution may be, okay, if you set a threshold that is very conservative, maybe you are under the risk aversion bias. Okay, you say, don't take risk, be safe. But after a false alarm, maybe that people are going to overconfidence, okay? While the many other people are looking only for the evidences that are supporting a given hypothesis. This is the confirmation bias, discarding all the evidences that are also very important to be taken into account. And okay, so the first phrase that the first statement that you will hear here that you will hear will be probably, okay, let's raise the thresholds. Okay, yes, a good idea. We have the experience. The landslide didn't collapse, so raise the threshold. This is not a good idea. And I'm showing you why. There are two slides. The first one, this is, why don't raise my threshold to 4 millimeters or 6 millimeters per hour? The overlap diagram on the right shows exactly why that logic fails. It plots the probability distribution of velocity for two populations. On the left, you have the non-collapsing slopes, the gray bell curve, the gray Gauss or Bell curve, and on the right, you have the collapsing slope curve. This is the orange one. The two distributions overlap partially, And that overlap is the root of all threshold problems. The vertical lines, the dashed one and this one is the 2 millimeters per hour threshold. Okay. Okay, the vertical. This shows you what happens when you shift the threshold. I'm showing you what happens if I shift the threshold. A step back. I'm stepping back. You have the 2 millimeters per hour threshold, and you accept to have this tail of the curve that are the false positive. This is you accept to have a percentage of false alarm. If you are shifting your the threshold towards the collapsing slope, you are losing, you are reducing the false positives, but you are entering the field of the false negatives. This is not free lunch, because if you lower the threshold, you catch more real events, but the false positive area, okay, is growing. But if you raise the threshold to reduce those false alarm and the false negative area, you begin missing real collapses. A false negative in this domain means that the system shows the green light while your slope is failing. That's not a credibility problem, it's a safety catastrophe. We are trading public safety for our ego. Can I say that? Okay, so the overlap region between the two distribution is not reducible. There is no threshold you can draw through it that eliminates both error types simultaneously. The distribution are not separable with a single cut. Okay. The second reason why is not a good idea to raise the thresholds is that if you look at the blue circles, these are the moments, the time where we are activating our monitoring system. And we don't know where are in the landslide evolutionary path. We, in reality, we are observing only a very short fragment of a process that started thousands of years ago. Many alpine deep-sea gravitational slope deformations are quiescent rock landslides originated in the post-glacial period after deglaciation, and stress redistribution. The problem is that we usually do not know where the landslide actually is along its creep evolution curve. A monitored acceleration may indicate an approaching failure, a transient response, a progressive adjustment phase, or simply a different rheological behavior of the rock mass. We don't know. So we have to keep our 2 millimeters per hour threshold. It is better to do that for safety. Okay. And in addition, likewise, a slowly moving slope is not necessarily a safe slope. So to structure the problem, we borrowed concept from medical diagnosis and clinics. And in medicine, it's called differential diagnosis. Okay. Having said that we have to keep active the 2 millimeters per hour thresholds, the only way to grow, to make our system, decision support system grow, is to integrate this information in a decision support system. So if we are looking to the medical experience, and physicians went into the risk management issues earlier than geologists, we look at a multi-evidence decision process. This approach allows us to collect different evidences that support or not a scenario, like a diagnosis. In this case, we integrate quantitative and replicable tests, okay, these data, semi-quantitative evidences like deep sensors, data coming from deep sensors, acceleration patterns, and rate of change trends, with a qualitative field observation. Okay, new cracks, rockfall frequency increasing, and drainage anomalies. This process must be transparent, repeatable, and auditable. So the shift is the foundation of our new procedure. To structure the problem, we borrowed, as I said before, concept from the medical diagnostic. Okay, and so the other concepts that we borrowed were sensitivity, specificity, and prevalence. The key point that I show you in the next slide is the prevalence of the phenomenon controls the predictive power of the first test, where the first test is the exceeding of the V24 threshold. Okay, using realistic values, the positive predictive value of the single test V24 is, I show you in the next slide. Okay, this is quite complicated, but we are approaching the end of my presentation, so please be patient. This slide introduces the core statistical problem that motivates everything we built. Okay, let's look at the single velocity threshold as a diagnostic test, like you see the COVID test, okay, the mouth swab that most of us used about 6 years ago. The central question is, like all diagnostic tests, it is imperfect. Okay, if an alert is issued only because V24 exceeds 2 millimeters per hour, what is the actual probability that the slope will collapse? Okay, so let's assume that the sensitivity is 100%, that is, every catastrophic landslide exceeds 2 millimeters per hour, and this is quite common sense. The specificity is the probability that a non-collapsing slope will not trigger the alert, and in this case we assume that the value of 80%, so we are assuming a 20% rate of false positive, as we said earlier. But which is the controlling factor is the prevalence of the phenomenon. Okay, most slopes in Valle d'Aosta in our region that move fast are not going to collapse. The prevalence can be taken from the regional landslide inventory, and this is the rate of collapse events in the Aosta Valley according to the national landslide inventory. Plug those values, those three values, inside the formula of the Bayes theorem. This is the so-called Bayesian engine, okay? And we get a positive predictive value of roughly 45%. In plain English, a single threshold alarm has a 53% probability of being actually a false alarm. it is less than toss a coin. Okay? This is when the prior probability of collapse is low, even a highly sensitive test will produce predominantly false positives. This is exactly the same problem faced in medical diagnosis. A screening test for a rare disease will flag many healthy patients. The takeaway, and this is the conceptual bridge to everything that follows, is that a single test is not enough. We need a sequential tests that progressively update our confidence. We need Bayesian updating. This is precisely what the decision chain on the next slide implements. What we are doing, we are collecting evidences that can support our prior hypothesis, where the prior hypothesis can be, is our landslide going to collapse or is not going to collapse? Well, the Bayesian approach updates the probability of collapse as a new evidence becomes available. Each observation, contextual, kinematic, and hydrologic deep deformation modifies our confidence. The goal is not to compute a perfect threshold. The goal is to build a decision architecture transparent, auditable, less biased, and more resilient. If you look at this slide, you will see that it is exactly what is being made in the field of weather forecast. We are issuing, the meteorological office issue a weather forecast, we declaring the confidence that they have in their forecast, and people accept this kind of communication. So if we only rely on a single threshold, we have 47%. But I assure you, believe me, that if you try to do that with a Bayesian engine that is to implement an Excel sheet, basically is very simple to do, only giving collecting another evidence that supports positively support our prior hypothesis raises the probability, raises our confidence to 82%. Okay, and the further decision elements are furtherly increasing our confidence. Clearly, I'm just kidding, saying that I won't wait to be at 96% to issue a civil protection alarm. 82% will be sufficient, and even more we won't wait for the 99.1%, because otherwise we would be crazy people. Okay, and I'm very sorry for the dimension of the fonts of this slide, just to show you how we translated this architecture in the procedure that is now effective to rule and to manage the Mont de la Saxe landslide. It is an official procedure. It is published in an official document, and if you want, I can send to people who are willing to the link to download this public document. And so we are going from green condition to yellow condition, orange and red condition. And when we are going into the red condition, we clearly have a very high confidence that is calculated and replicable, and we can make our decisional process transparent. Okay, lesson learned. this is the more or less the closing loop. Mitigation, residual risk, takeaways. A monitoring system is the one of the pillar of civil protection system, mostly when we have a very critical situation with high stake, high value assets, not only people, not only public safety, but also economic interest to be protected. Okay, and with this reflection and with these takeaways, we also being able to review and improve the procedures that are ruling the monitoring system of our other 5 other great big landslides that are on the Valle d'Aosta territory. They have volumes that are more than 1 million cubic meter each one. They threaten both infrastructure and hamlets. So you in all of these cases you have to ensure public safety and economic interest and we strongly reduced the false alert. And so we strongly reduced the cry wolf effect because, a civil protection system is a system that is piling up public confidence, public trust during peacetime, only to spend it during the emergencies. And so cry wolf effects is eroding the public trust in the civil protection system. So to build reliable monitoring systems and that are the core of the larger early warning system is a long-term investment that is paying when we are dealing with emergency. And this is another answer that I'm very interested to show you. We could apply this kind of approach also to monitoring an active glacier that is threatening a very touristic valley in Aosta Valley. It happened in summer 2025, so last year, and also in this case, we were able to reduce the discomfort during the high peak touristic season, because in this case the glacier are prone to accelerate in August and July, that are the high peak season in Italy. Well, just in the end, the takeaways is that monitoring is necessary, but it is not sufficient. Thresholds alone are unreliable in complex multi-domain systems. Integrate monitoring makes scenarios observable. Hydro process often dominate the behavior, and mitigation must be measurable and validated. But the objective is not to change the threshold, is to build a system and systems that could be auditable and transparent. Okay, and I'm astonished. It is 1 hour. It is 1 hour, and I'm done. Thank you very much for your attention.